Okay, so if not, then today we're talking about continuity. So at the end of class on Friday, we saw the definition of continuity very briefly. So I will remind you of that today, and then we're going to spend the whole day today doing examples of how to decide whether or not a function is continuous. So we'll revisit some of those examples that we saw a few weeks ago that it wasn't so clear whether or not they were continuous, and we'll use the tools that we have now to decide whether or not they are. Okay, so here was our definition. Let's let f be a function, and we'll let a be a real number. Then we're going to say that f is continuous at a if the following holds. So the first thing is that we need for f of a to be defined. And then the second thing is sort of the more involved condition that uses collapsing collections. So given a two-sided collapsing collection, for the number a, then here's what we're going to do with that collapsing collection. We're going to take the f images and then compute the wrappers of those f images. And if the wrappers themselves also form a collapsing collection, then the function's continuous at a. So given a two-sided collapsing collection for a, the wrappers of the f images of the collapsing collection. I'll write this out. Are a closed collapsing collection for that value f of a. Okay, so we stick in a collapsing collection, take the wrappers, and then we're hoping, if we want the function to be continuous, then we're hoping to see that the outputs are also a collapsing collection for the value f of a. Okay, so this is a mouthful, but we'll get a lot of practice with it today. So let's take this definition and turn it into sort of a recipe for how to decide whether or not a function is continuous. So here's like how to decide if a function f of x is continuous at some value a. Okay, so looking at the definition, the first thing that needs to be satisfied is that f of a is defined. So I'm going to call that as step 0, is that we just need to check quickly whether or not the function is defined at that value. So, here's step 0. Check if f of a is defined. Okay, then we need to check this other condition. So what we're going to do is start with a collapsing collection. And actually, the cool thing is that it doesn't matter what collapsing collection you choose. So you can pick whichever one you want. And as long as it's true for one collapsing collection, then it will also be true for any collapsing collection. And the book talks a little bit more about the details of why that's true, but the main point is that you get to pick whichever collapsing collection you like, or maybe whichever one might suit the problem the best. Okay, so the first thing we need to do is choose a two-sided collapsing collection. Oops. Oh my gosh, there's like some part of my iPad that isn't picking up the writing. Okay, so we're gonna pick a two-sided collapsing collection for A, C1, C2, and so on. Okay, then what do we have to look at? We need to compute the wrappers of the F images. So we'll do that in a couple of steps. So the next step is to find what F of each of those intervals is. So these are the F images of the intervals C1, C2, and so on. Okay, and then once we have the F images, we have to find the wrappers. So 3, find the wrappers, which was denoted brackets FC1, FC2, and so on. Okay, and then the last thing is we want for this collection, so this is automatically, it's going to be a collection of closed intervals because the wrapper is always a closed interval. So we have some collection of intervals here, and we want to check whether or not that is a collapsing collection. Okay, so recall when we want to check whether or not something's a collapsing collection, we have to check two things, right? What's the first thing to check? Yeah.
There's one point contained in this.
Yeah, so we need for there to be at most one point contained in all sets. Oops. And then what's the other thing that we have to check? Yeah. Yeah, so we also need to check whether each interval is contained in the previous. Okay, so these are like the two things that we're interested in. I'm gonna look at the second one for a second and think about this. So the second one is always going to be automatically satisfied. Why is that? So we stuck in a collapsing collection to start with, right? Which already satisfied this second property. So let's look at this. So we have C1, which contains C2, which contains C3, and so on, right? And then what we want to look at is the wrapper of the F images of these. And we want to see that same chain of inclusions. So let's say I have a point that's in C2. So let's say like X, let's say I have some element X in C2. Oops. then f of x will be in the f image of C2, right? But that means, so since x is in C2, it's also in C1, and that means that when I take the f image of C1, it will also contain f of x. Is this making sense? So as like an intermediate step, so let me move these down. So what I'm claiming is that the f images of my collapsing collection automatically satisfy these containments. Does that make sense? Because like, okay, let me just explain this one more time. So what is in f of C1? This is the outputs of f across all elements of C1. But since C1 contains C2, that means that this already contains the outputs of f across elements of C2. Does that make sense? Okay, so then we want to look at the wrappers. And the wrapper is just the smallest closed interval containing each of those sets. So the smallest closed interval containing this one will automatically contain the smallest closed interval containing f of C2. Right? Say like the wrapper of f of C2 had something extra in it, well, that would also have to be inside of this one. There's really no way for this to like pick up something that's not already in here by just taking the wrapper. Okay, so the point of this is that this condition is automatically satisfied, so you never need to check it. Okay, so we can just so I'll move this down and I'll just say, like, note, we do not need to check this part in order to see if something is, in order to see if your function is continuous. Okay, does that make sense? Are there questions? Okay, so then going back to our procedure, the only thing that we need to check is whether or not the only point that's contained in each of these is, we want that to be f of a specifically. So I don't just want that there is at most one number in all of them, but specifically I want to see that f of a is in there. So let me rephrase this. So we want to see that the number or the value f of a is the only number contained in each of these wrappers of the f images of our collapsing collection. Okay, so these are the steps. So we'll do this for a bunch of examples today. Are there questions before we jump into the examples? Okay, so let's do the examples. So for our first example, let's look at just a linear function. Let's look at L of x is equal to 2x, and we have to decide whether or not it's continuous at a specific value. So we'll look at x equals 3, say. Okay, so going through the steps, step 0 is L of 3 defined. Yeah. Okay, so we're happy with this. So, right, there's no issue with plugging in x equals 3 into this function. So, it is defined at x equals 3. Okay, so next step, now we have to choose a collapsing collection for 3. So it has to be a two-sided collapsing collection for 3. Do you all have any particular preference? I kind of like the reciprocals one. Let's go ahead and do that. So we'll do, 3 minus 1, 3 plus 1, 3 minus 1/2, 3 plus 1/2, 3 minus 1/3, 3 plus 1/3. By the way, like, when I'm writing these out, you could simplify these if you want to, but honestly, I think it's easier to see the pattern if they're unsimplified. So that's why I leave it like that, just so that it's clear what's happening at each step. So you really don't have to simplify these. Okay, so then the next thing that we have to do is take the L images of the intervals. Okay, and at this stage, it might be helpful to make a little sketch, because as we saw with when your function, in some cases, you cannot just compute the image, sorry, you can't just compute the image of the interval by plugging in the two endpoints, right? Sometimes that won't work. Like if you're, so the example that we did was with the parabola, if you take an interval, so if I have a parabola and I take an interval surrounding this sort of minimum, then the F image will be an interval like that on the y-axis, where the endpoints, if you just plugged in the endpoints, that would tell you that there was only one value in the image of the function, which just isn't true. Okay, so I'm going to make a little sketch of the function. So it's going to be a line with slope 2. Oops. And we're looking at x equals 3. And so for my intervals, I'll draw the first one in green. So it's like from 2 to 4. So the F image of that interval, we can just use the lift and project method to see what it would be. And it looks like in this case, the interval is just given to me by those endpoints, right? There's kind of no funny business going on inside of this part of the graph that would make the value higher or lower than it is on the two endpoints. So here, we do just get that this endpoint is given by L of the left endpoint of the interval from below. So maybe I'll call this A and B. So this is just L of A, and this is L of B. Does that make sense? Okay, so that means that I just need to apply the function to each of these numbers. So here I'll get, so we're just multiplying everything by 2. So I get 6 minus 2, 6 plus 2, 6 minus 1, 6 plus 1, 6 minus 2/3, 6 plus 2/3, and so on. Okay, then, are there questions about that stuff? Yeah.
Yes, why would it-
Oh, that's just because the function is just multiply x by 2. Yeah. Right. I'm just plugging it into the function. Yeah.
I guess I have a fast question.
Yeah.
So is the, like, I guess I'm wondering, is this picture we're drawing here, is this like a explanatory device, or is this what would constitute, say, like in the context of the exam, like a rigorous proof, like you can kind of say, like, okay, I've like definitively argued this, like just like what was kind of losing me a little bit is because it's like an infinite series, right? Like how much, like how many elements do you need to sort of take before you can say this has been like definitively shown rather than just kind of like intuitively demonstrated?
Yeah, I think so that's a good question. So as far as this, like, you know, using this picture, am I convinced that if I want to compute the F image of any interval in this sequence, that like this is the process to do it? And I think that like for this one, yes. You know, obviously they'll get more complicated and we might need to make more of an argument here, but I think for this one, like this is totally fine. Just some kind of explanation of what your process was in figuring out what the F images of the intervals were.
Okay.
Are there other questions? Okay, so then step 3, we need to compute the wrappers. So for these, what is the wrapper going to be? Yeah. Yeah, so whenever you have an open interval and you want to take the wrapper of it, all you need to do is change it to a closed interval. So for these, it's pretty simple. So we'll just have the closed intervals. Okay, then the last thing that we need to determine is f of 3, oh, sorry, it's L. Is L of 3, which is 6, the only number contained in all of these intervals? What do you guys think? Looks like maybe yes. So I think there's options for how we could argue this. The way that I was thinking about this was to use the reciprocal of radius rule. So if you remember, we had a rule for showing whether or not something is a collapsing collection, where you just compute the distance from this number to the endpoints, take the maximum one. In this case, it's symmetric, so it'll be this just whatever this distance is, and then take the reciprocals. And if that is an unbounded set then this is a collapsing collection. Okay, so let's do that to get practice. So the radii with respect to six of the intervals are 2, 1, 2/3, and so on. So maybe we should say what the dot dot, maybe I'll give a few more of these dot dot dots. So we get so it would have been 1/4 that we were plugging in there. So we're getting 2/4, 2/5, and so on. So then the reciprocals, maybe I'll pause. Does it make sense how I got these numbers? No. Okay, so that's just the number that I'm adding or subtracting from 6 at each step. And that's, in this case, that'll be the radius of the interval. Does that make sense? Okay, so then the reciprocals are 1/2. So I'm just doing 1 over those numbers. So maybe I'm gonna write 1 over 1 more suggestively. So this will be 2/2. 4/2, 5/2, and so on. Okay, do the reciprocals form an unbounded set? Is there a single number that's larger than every number in this list? No, because like, okay, so say you were like, okay, what about 1,000,000? That seems like a really big number and it could be bigger than all the numbers in this list. Well, somewhere out here we have 2,000,001/2, right? And that's bigger than the number. So this is an unbounded set. So by the reciprocal of radius rule, this is a collapsing collection. I'm just gonna copy it. Okay, so that means that the function is continuous at 3. Yeah, did you have a question? So, for example, if so yeah, let's draw, I'm just gonna draw a little picture to the side. So if the reciprocals did not turn out to be a bounded set, they could be approaching some fixed number. And how that would look would be that your intervals were doing something like, let me give an example. So let's say the left endpoint is getting closer and closer to -1, and the right endpoint is getting closer and closer to 1. Then, so say something like -1, -1/3, 1 + 1/3. That would be like, oh, sorry. So something like this, -1, -1, -1. Okay, so this is not a collapsing collection, right? Because there'll be a whole bunch of numbers that are contained in every single interval. So namely, like the entire interval from -1 to 1 is contained in every single one of these. And that's how it might look if your radii don't form an unbounded set. Yeah. Are there other questions? Okay, let's do an example where the function is not continuous. See how this goes. Right, because it seems like we didn't, at the end of the day, like we sort of already knew that this thing was meant to be continuous because we can draw it without picking up our pencil, right? So let's check whether or not like the technology that we've created works on examples that are more complicated. Okay, so let's do this example. So I'm gonna let R of X be, you guys want to do the removable discontinuity or the jump discontinuity? So just as a reminder, removable looks like you have a hole and then a different value, and then jump is like you have something like that, and then you jump to somewhere else and you have some other function. Do you have a preference between those two examples? Removable? Okay, sounds good. Let's do removable. Okay, so we'll make R of X equal to, it'll be 2x when X is not equal to 3. And it'll be 9 when X is equal to 3. Okay, so let's run through the steps again. So 0, we have to check whether or not this function is defined at X equals 3. Oh yeah, we're gonna do this at X equals 3. Okay, so we have to check whether or not the function's defined, and it is, right? Like we know if I put in X equals 3, then I know what the output of the function should be. So R of 3 is equal to 9. So it is defined. Okay, and then we have to pick a collapsing collection, and I'll just pick the same collapsing collection that we had in the previous example. So we had 3 minus 1 to 3 plus 1, 3 minus 1/2, 3 plus 1/2, 3 minus 1/3, 3 plus 1/3, and so on. Okay, now what are the R images gonna be? Here we're gonna get something a little bit weird. So let me draw the sketch again. So we have up to, say this is X equals 3. Then we get a hole. And then the value there is 9. So it looks something like that. Okay, so here's what will happen is if I take an interval around 3, then I get something like that. But remember, so I'm shining a light up from this interval towards the graph and coloring in everything. So the light will shine and hit this hole, or the point that's on the other side of the hole. So that is in there as well. Okay, so then then I'll project it to the y-axis. So I get this point, which is 9, and then something there, and then a hole at 6. And then we go down to that endpoint. So let's say this is AB. So this would be 2A, and this is 2B. Okay. maybe I'll pause. So this was something, I feel like this goes back to the question that you were asking at the last example. So if my interval is large, then when I do this, I guess something like that, right? And I would, so the whole, that would be there, but it wouldn't be like separate from the rest of this set. You see what I'm saying? So if I take big intervals, you see a slightly different behavior when I compute the F image than when I start to take smaller and smaller intervals. But the point is the intervals are getting smaller and smaller. So eventually the behavior will look something like this. And this does describe what happens for all of the remaining intervals. Does that make sense? So it could be that the first few terms, the first few intervals are a bit too big and they don't really describe the general situation, but eventually your intervals will be small enough that the same thing is happening. Okay, so what are the F images, or sorry, the R images? So looking at this picture, I'm gonna get, so for example, for this first interval, I get an interval like this, right? And then a small hole, another interval, and then a singleton. So we would get, and sorry, this A to B should be an open. So this should be a little hole like that. Okay, so I'm getting the interval from, so this is 2 to 4, and I'm gonna multiply those by 2. So I get 2 to 6 union 6 to 4, or sorry, 6 to 8 union the singleton containing 9. Does that make sense? How I got that? Yeah. Yeah, so let me zoom in on this picture a little bit because I made it kind of small. So when I compute this F image of this interval, right? I'm gonna highlight everything on the graph that sits above the interval like that, and then project it leftwards to the y-axis. But I get a little hole right here, right? So the value of the function should be 6 right there, right? Because 3 times 2 is 6. But that value isn't actually achieved for any of these inputs. Like the function just skips that value. So we just get a little hole here. So I get an interval from there to 6 and then 6 to whatever the right endpoint is. Does that make sense? So yeah, for this first one, we had 2 to 6 and then 6 to 8 and then that singleton containing 9. Okay, so then the next, are there questions about that? Okay, so let's write down the next interval. And I think I'm not going to simplify this again because I think it at least made it harder for me to remember what was going on. So we'll get, for the next one, 6 minus 1 up to 6 union 6 plus 1. Oh, sorry. 6 up to 6 plus 1 union that singleton containing 9. Okay, let's do one more. So I'm just doubling this number, making an interval to 6, starting a new interval at 6, and then doubling this number. So 6 minus 2/3 up to 6 union 6 plus, so new interval 6 to 6 plus 2/3 union singleton containing 9. It continues like that. Okay, are there questions about that? About how to compute those R images? Yeah,
How would you do it from just like the plugging in standpoint versus like the graphics standpoint?
so with this one, you mean like, and just in terms of plugging in the endpoints?
Like if you're looking at RLX without the graph, like just without it, how would you like go about doing the images if you didn't have the graph?
So if you wanted to do this without a picture, you could, let's say we wanted to compute the R image of this interval. Well, we would break it up into cases, right? So we have like the numbers that are less than 3, the numbers that are equal to 3, and then the numbers that are greater than 3. And then you can decide what happens in each of those cases. And that is kind of reflected in how these come out, right? So we have like what happens to the inputs that are less than 3, what happens to the inputs that are greater than 3, and what happens to the inputs that are equal to 3. Yeah. But I do think that probably the most straightforward way is going to be to try and graph the function and then use the picture to get the images of the intervals. Are there other questions? Yeah. Yeah, so we're checking, yeah, is this function continuous at 3? Oh, yeah. So I think 3 intervals is enough to kind of see what the pattern will be. Yeah. Okay, other questions? Yeah.
Can you just explain about the number of one?
Yeah, maybe I'm gonna rewrite this interval too, because I think this made it more confusing. So this one would be 6 minus 2. So like where are these minus ones and plus ones coming from? Yeah, so that was, I'm plugging in this interval into the function. So like what happens to this left endpoint? That's A in this picture. So that gets, the function is when x is not equal to 3, just multiply by 2. So I get 2 times A in my output. And so here I'm just multiplying this number by 2, so I get 6 minus 1.
Okay.
Yeah. Okay, let's compute the wrappers. And maybe actually for a second, let's just notice like the output of this was kind of wacky, right? Like in the previous example, we got something that was really clean. And here now we have this discontinuity and the R images already are kind of a mess, right? So now we're gonna take the wrappers. So the output of that will still just be a closed interval, but it's going to contain too much stuff to be a collapsing collection. So let's see what happens there. So we have to compute the wrappers. What is the wrapper of the first set going to be? So this first element in the collapsing collection, what is its wrapper? Can you say that again? Yeah, so it'll be the closed interval starting at the smallest point in this set up to the largest point in this set. So it'll be the closed interval from 6 minus 2 to 9. Does that make sense? So yeah, for the wrapper, again, we're just shrink wrapping the whole set. And so if you can figure out what is the smallest point in the set and what is the largest point in the set, then your answer is just going to be a closed interval from one number, from the smallest number to the biggest number. Okay, so then the next one we would get the closed interval from 6 minus 1 again up to 9. And then we get 6 minus 2/3 up to 9. And I'll just write a few more terms in here. So we would get 6 minus 2/4 to 9. 6 minus 2/5 to 9, and so on. Okay, so final step. Is R of 3, which is 9, the only number contained in all the intervals? No. What's another number that's in the intervals? Yeah, 8 would be in all the intervals, right? Because, so clearly 8 is in all of the intervals that I've written down, but also this is just gonna get closer and closer to 6, right? This will never be, greater than 6. We're always just subtracting the time quantity. So 8 will for sure be in all of the intervals. So, no, since 8 is in every interval. Because the left endpoint are always less than 6. Okay, so then the conclusion is that the function is not continuous at x equals 3. Okay, are there questions about that example? Okay, so let's end things there. On Wednesday, we'll do the wiggly function that we saw a while ago that we weren't really sure whether or not it was continuous. So we'll use this to decide whether or not that function is continuous. And yeah, I'll see you then. Yeah. Anyone, I think people are still writing.
Why did you just
Yeah, this is some of that question before. Like, outside of the ball, like, what kind of contribution good? So, yeah, I guess I'm wondering if there was sort of an argument that occurred to me intuitively how to include that thing, and I'm wondering why it's like similar. Sort of wondering like, what's the need to kind of go to the additional degree of frequency, right? So like what I was kind of thinking as well, every real number has every real number that's bigger than 0 has a number that's closer to 0 than it is, right? And it seemed like you could just use that to show that, and it's to do with the radius rules, kind of in that example.
Yeah.
But then, so I'm thinking to myself as well, we use the radius rules, so there must be some need to import that additional complexity. I'm just wondering what that is for purposes of understanding what's different.
I think either is good.
Okay.
It's going to the radius rule because it's like something that we did, and it's like one that was in a toolkit, and so it's less like ad hoc maybe, but like what you said also works.
Is there anything you'd recommend, like additional reading to kind of develop a stronger intuitive sense of like what's a good mathematical argument for purposes of a proof? I just feel very like kind of shaky on it. Like,
Have you looked at the book?
yeah.
I think the arguments that are in there are pretty clear in every step, so I think those are like good examples. Yeah. I don't think I could. For the, I know how I got the, okay, so this was the, oh, it's gone. Okay, fine. Yeah,
That's about like the testing agreement for extra time.
yeah.
The reason it's still processing it said that like talk to you about it. For Thursday. I was wondering,
As far as I know, you should be able to schedule everything completely through SAS. Like, there's no approval required on my end, I don't think.
yeah, I did that. And then it says, please contact your instructor to fill out the agreement.